Welcome. Today, we're diving into some key building blocks of data analytics: vectors, matrices, and arrays. These data types form the foundation for working with complex information and performing linear algebra operations. Let's explore how they fit together and why they matter in analyzing data effectively. Let's dive into the basic data types in R, starting with logical values. These are just true or false. Then, we have character data, which is text enclosed in quotes. Next up are integers, whole numbers marked with an L, like 5L. Finally, numeric values represent real numbers, like 3.14, and they're the default type for numbers in R. Understanding these types is key to working effectively with vectors, matrices, and arrays. Let's start with vectors, the fundamental building blocks in this data world. Here, we have a simple vector containing four numbers, 2, 4, 6, and 8. When we check its class, it's numeric, meaning all elements share the same type, and its length is 4, matching the number of elements. The key takeaway: a vector holds one type only. This consistency makes vectors powerful and predictable as we build more complex structures. Let's talk about matrices, a way to organize values into rows and columns. By default, values fill column by column, but if we set by row to true, they fill row by row instead. For example, creating a matrix with numbers 1 to 6, 2 rows, and by row set to true, arranges the numbers across the rows first, then down the columns. This gives us a clear, structured grid of data to work with. Let's talk about nomming and accessing elements in a matrix. Here, we assign names to the rows R1 and R2 to make referencing easier. To get a specific element, like the one in row 1, column 2, we use square brackets with those positions. If we want the entire first row, we leave the column blank. Similarly, to get a whole column, we leave the row blank. This way, we can quickly pull out exactly what we need from the matrix. Let's take a closer look at some key matrix operations in R. When we write a plus b with a plus sign, we're doing element-wise addition, adding each corresponding entry. The %% symbol means matrix multiplication, which follows the rules of linear algebra. Transpose flips the matrix over its diagonal, swapping rows and columns. Solve finds the inverse of a matrix, if it exists, and det calculates the determinant, a value that tells us important properties about the matrix. These computations are the foundation for working with matrices in data analysis. Arrays take the concept of matrices a step further. They let us work with 3 or more dimensions. Think of them as multi-layered grids, where each dimension adds a new axis. We define their size using the dim parameter, which sets how many elements go along each dimension. For example, creating an array with dimensions 2 by 3 by 4 lets us organize 24 elements in a structured way. Accessing elements is just like with matrices, but now we specify the position in each dimension. Let's take a closer look at two important operations with arrays: the outer product and the generalized transpose. The outer product combines two vectors to create a matrix. Every element of the first vector multiplies with every element of the second. Then, the generalized transpose rearranges the dimensions of an array, not just flipping rows and columns like a simple transpose. These tools help us manipulate data structures in flexible ways, essential for working with multi-dimensional data. When we want to combine data in R, two functions come in handy: cbind and rbind. Cbind sticks matrices or vectors side by side column-wise. Rbind stacks them one on top of another row-wise. So, cbind, A, B joins A and B by columns, while rbind, A, B joins them by rows. Just remember, the dimensions have to match up properly for these to work. This is a key technique when working with vectors and matrices. Now let's look at solving a simple linear system. We have a matrix A and a vector. Our goal is to find the vector that satisfies the equation A times x equals b. Using the solve function, we plug in A and B, and it returns the solution vector. In this case, x equals 1 and 3. This is a fundamental step when working with matrices. It helps us find unknowns efficiently. That wraps up what we've covered so far in Unit 4. We've looked at how R handles different data types, from numbers to characters. We explored matrices and arrays, and how to combine and manipulate them with functions like cbind and rbind. We also touched on indexing and key operations like matrix multiplication and transposition. Next, we'll dive into lists, factors, and data frames in Unit 5. This video was created with SlideSpeak. Visit SlideSpeak to turn your presentations into engaging AI-narrated videos.